We're going to end this lesson with a couple application problems. Example 4 says the value V of a Chevy Cruze LT that is T years old can be modeled by, and we have our function here. According to this model, when will the car be worth $12, $9, and $3,000? So because we want to know when, that means we are solving for T. We're solving for our time. That means this right here, that these represent your V, the car's worth. Now, one thing we could do is we could plug in 12,000 into our V and then solve it for T. Plug in our 9,000, solve for T, and then plug in our 3,000 and solve for T. Or just take this equation here and rewrite it where you have solved for T, and then it's just substituting in these three values. So I'm going to rewrite this down here where I don't have V of T, just V. And now let's solve this for T. So first thing we need to do is isolate the exponential. This is my exponential right here. So this is 19,200 times my exponential. So the first thing I'm going to do is divide that over. So we're going to have V over 19,200 equals 0.82 to the T. Now this is isolated. Now we can rewrite. So base of the exponential, which is 0.82, to the other side of the equals. So we have log base 8.2 of V over 19,200. And that's going to equal what's left over, equals my exponent of T. So we have T equals. And so that is now solved in terms of what we need to find, when. So now this is just substitution. If you don't have an 84 and you have an 83, you're going to have to use your change of base here. So log of V over divided by log of 0.82. But if you have your calculator, if you have your 84, we're going to go alpha window, number 5, 0.82. My V, if we start with A, is 12,000 divided by 19,200. And after about 2.4 years, the car will be worth 12,000. Go up here and edit and change this to 9,000. And then change it to 3,000. So there's your A, B, and C. It's worth 12,000 after about 2.4, 9,000 after about 3.8 years, and 3,000 after 9.4 years. Okay, example 5 is maybe a little bit harder of an exponential, but not really. And that's going to the same thing. So the resident population of the United States in 2018 was 327 million people and was growing at a rate of 0.7% per year. Assuming that the growth continues the model, we have P of T equals, where it represents the population P and millions of people in year T. According to the model, again, when will the population be? So these represent my P. We want to know when, we need to solve for T. So instead of plugging this in and solving this equation twice, just rewrite this equation in terms of T. So I'm going to rewrite this down here. And now let's solve for T. So step 1 is to isolate the exponential. This is my exponential. So this is 327 times my exponential. We're going to divide that over. So P over 327 equals 1.007 T minus 2018. Now that I have my exponential isolated, let's rewrite. So we're gonna go base of my exponential to the other side of the equals. So we have a log with a base of 1.007 of P over 327. And that's going to equal what is left over, my exponent or my exponent here, T minus 2018. Step 3 is to solve. Now, last time when we rewrote it, it was already solved for T. Now it's not solved for T. So now I need to add that 2018 over. So we're going to have T equals log of 1.007 of P over 327. I'm adding it over, so plus 2018. So now I can substitute these in and rewrite and solve it. So out the window for number 5. We have a base of 1.007 of P. My first P is 415 divided by 327 plus 2018. And the year 2052, we will have about 415 million people. Change that. The 470, and about 2070, we'll have 470 million people. Okay, and for the record, I get this sometimes. When I am putting in these numbers here, I don't need all of these zeros here because it tells me here that my population is in millions of people. So that 327 million people is just represented as 327. So you just know that there's, millions. We're just cutting off all those zeros altogether. So there you go.